Hello everybody, this is Potato, and I have been getting a flood, a barrage, no, an absolute torrent of comments, all asking me the exact same question. And that is, Potato, how are you so gosh darn good at math? And the answer is, I use a calculator. First we need to understand the language it speaks. Now you probably know that we use a base 10 system for numbers, and what that means is the value of a number depends what place it is in. So for example, the number 94752 isn't just 9 plus 4 plus 7 plus 5 plus 2, because that would be a terrible way of representing big numbers. Instead, the 9 represents 9 times 10,000, and the 4 is 4,000, the 7 is 700, the 5 is 50, and the 2 is just 2 because it's in the first digit. Now if you think that's pretty simple, then I have some good news for you. Binary is even simpler. Because you see, all binary is instead of using powers of 10, which is a big number, we use powers of 2, which is a small number. In fact, it's the smallest number you can use to make a base system. So instead of 10,000, which is the fourth power of 10, we're going to use the fourth power of 2, which is 16. Instead of 10 to the third, we're going to use 2 to the third. Instead of 10 squared, we're going to use 2 squared. And then instead of 10 to the first, we're going to use 2 to the first. And 10 to the 0 just so happens to be the exact same as 2 to the 0, so we get to keep that the same. Now you may have also heard that binary is just comprised of ones and zeros, and that's true, so that means these numbers we have up here are not going to work. Instead, we can use an example like maybe 1, 0, 1, 1, and 0. And because it's binary, these are the only two digits we can use. That means either we have a number or we don't. So in this case, the numbers we have are 16, we have 4, we have 2. And so 16 plus 4 plus 2 is going to make 22, which means 10110 represents 22 in binary. The reason why this is useful, of course, is because redstone operates in binary. Redstone is either going to be on or off, and so depending which levers we flip or which redstone lamps are on, that's going to tell us which binary numbers we're dealing with. Let's see this calculator in action. What I've done is I've got a bunch of different numbers that we can try to add together here. I'm going to be placing them into these droppers here so that we can get a random number each time, and we're going to try to add them together using that giant calculator I just showed you. So let's put these all in. Oh, not that one, that's my pickaxe. And hopefully if we just flip the levers, we should get two numbers. We get 15 plus 15. Okay, so it looks like these droppers are trying to make me do the maximum. Let's do it. So for 15, we're going to actually do 8 plus 4, that's 12, plus 2 more for 14, and plus 1 more for 15. And because the other one gave me 15, that means I need to flip all of these as well. And now hopefully 15 plus 15, well, that should be 30. And that can be represented using 16 plus 8 plus 4 plus 2, which means all of the lamps over there should be on except for the one. You can see we have 16 plus 8 plus 4 plus 2, which makes 30. Let's try that again just to see that it wasn't a fluke. All I have to do is flip these levers a couple of times to get some new numbers. So we have another 15, that's surprising, and a 12. And so the first number is actually the exact same, I don't need to change that. The 12 is going to be 8 plus 4, so we can leave these on, but 2 plus 1 needs to go away. And now we're doing 15 plus 12, well that's 27, which means if we think about it, that's going to be 16 plus 8 plus 2 plus 1. And so basically all of the lamps should be on except for the lamp representing the number 4. See, 16 plus 8 plus 2 plus 1, that makes 27. Let's try this one more time just to make sure we got the hang of it. So let's get some new numbers. This time we have 7 plus 9. So let's try adding together some smaller numbers to see if it works. We can reset all the levers back to 0, and then we do 7 by adding 4 plus 2 plus 1, and then we're going to make 9 by adding 8 and 1. And now 7 plus 9 should make 16, which means only the lamp for 16 should be on, and all the other ones are going to be off, as we see here. So our calculator is working exactly as intended. Now, to understand how we build something like this in Minecraft, we need to start with some relatively simple logic gates. Now, a logic gate is going to be a relatively small redstone components that might just take 1 or 2 inputs and gives you an output. So for example, one of the simpler ones would be a NOT gate. We can use this lever as our input. We'll use a piece of redstone dust, and then all we need to do in Minecraft is run that into a redstone torch, and what a NOT gate is going to do is invert the signal. So if the input is off, then the output is on, and then if we turn the input on, then the output turns off. Now we can try another one. Let's make an OR gate. So an OR gate is going to have 2 inputs, and the goal is we're going to try to make our output turn on if either one of these are on or if both of them are on. Now there's actually a very simple way to do that in Minecraft, which is just by putting 2 redstone wires together. You can see now, if we turn one of them on, the lamp turns on. If we turn the other one on, then the lamp is still on. If we turn them both on, the output is still good. But if both of them are off, then the lamp turns off. Now, in terms of Minecraft, there is a slight problem with what we have here actually, which is the fact that the signal can go back up the wire and mess with the things back down the line. For example, if we're trying to run this into multiple things, well then you can imagine, maybe we have a NOT gate over here, and suddenly that gets triggered because the signal from this input is going all the way through the wire and into that. So we can fix that by adding a couple of redstone repeaters, and we're going to have to keep that in mind when we're putting these components together. Now the last thing we're going to try for logic gates is an AND gate. Now an AND is going to have 2 inputs again, and this time we want the lamp to only turn on if both of these inputs are on. And so if the levers are like that, the lamp should turn on, but if the levers are anything else, let's just say one of them turned on, then the lamp should be off. And it's a bit tricky to figure out, but it turns out you can make an AND gate by combining NOT gates and OR gates. We can have 2 NOT gates, like this, using redstone torches. We can make an OR just by putting a piece of redstone dust in between them, and we make another NOT with a redstone torch. And if we do some testing, we'll see that this does exactly what we want from an AND gate. If we turn just one of the levers on, you can see this redstone dust is still on because of this torch, indicating that we need both levers to be turned on in order for this lamp to turn on. And so again, if we only have one lever, it's not enough for the lamp to turn on. We need both of them. And obviously, if one of them is off or both of them are off, then it does not work. Alright, so to understand how we're going to put together these different redstone logic gates into sort of more complicated redstone components, I'm going to have to introduce you to 3 different types of adders. There are half adders, full adders, and death adders. That last one is a joke. Now what a half adder does is it's going to add 2 different digits. So there are going to be 2 outputs, and what you'll notice about that is if both of them are on, which can be represented with a 1 and a 1, well, we want to, of course, add them together. And that's going to make, wait for it, 2, yes. That's represented with a 1, 0 in binary. Now that's actually a 2-digit number, which means this half adder is going to have 2 different outputs. We're going to have the first digit, which we're going to call the sum, and we're going to have the second digit, which we're going to call the carry, with a little c up there. Now, let's see how this looks. We're going to have 2 inputs. Like I said, let's call them P and Q. And if we make a little table off to the side here, let's try to figure out precisely what we're trying to have this half adder do for us. So if both P and Q are off, then obviously this should give us a 0, which is represented with a 0, 0 in binary. If one of them is on, let's say Q is on or P is on, then we're going to have the sum turn on and we're going to have the carry off. So this is 1 in binary. It's the same as 1 in base 10, actually. And then lastly, if both of them are on, let's say with a 1 and a 1, then we're going to again need the number 2, which means this is where we have a 1 and a 0 coming out of the half adder. So to understand how to do that, let's focus on this column of the table, the sum. What you'll notice is that the sum turns on if P is on or Q is on, but not if both of them are on. So first, let's see how we test if both of them are on. Well, that's going to be an AND gate, right? We can connect these both into an AND gate, which I'm going to represent with this symbol here. And we're going to take the output from that. Now remember, we're trying to see if these two are not on. In other words, if these two are on, then we want this one to turn off. And so the way we're going to do that is by branching off a NOT gate, which I'm going to draw with a little triangle like that. And then we also need our OR. Remember our observation of this column of the table was that we want it to turn on when P is on or Q is on. So I'm going to have this wire come over here. I'm going to draw a little loop to show that they shouldn't interact with each other. So we have our 2 inputs going into an OR, which I'm going to draw with this sort of shape, or at least try to. So that's our OR. And if we think about it, we need our OR to get triggered, again, by either P or by Q, even though I said that in the wrong order. And then we also need P and Q to not both be on. So in other words, if they're both on, then it's going to go down into this NOT gate and turn off. And so really, what we want is to combine these two using one last AND gate, and the output from that is going to be our sum digit. Then the last step, is to do the carry digit, which is much more simple. You see, the carry only turns on when both P and Q are on, which means we can really just take our output from the AND gate, take it out, and this is our carry digit. Just to check that this is working the way we want it, let's try an example. Let's say P is on and Q is off. So we're looking at this row of the table. So if P is on, but Q is not, then this AND gate right here is going to be off because Q is off. And remember, we need both of them to be on in order for it to trigger. So this is going to give no output and our carry is going to be 0. Meanwhile, down here, our OR gate is going to turn on. Why is that? Well, because remember we have P on and we have Q off. And for an OR gate, only one of them needs to be a 1 in order for it to give an output. So this is going to be on. Meanwhile, if we look at this NOT gate, it's going to be the opposite of the signal it gets. So this is 0, the opposite is a 1, And now we have two 1s feeding into this AND gate, which is exactly what it needs to turn on, which means the sum turns on. And you can see these two digits that we got correspond perfectly with this row of the table, which is what we wanted. And I'm not going to do it in this video, but if you were to do a similar test with all 4 of the rows of this table, you would see that the half adder does exactly what we want it to do. So back in Minecraft, let's see what a half adder actually looks like, because this is where things can get a little bit tangled, so stay with me. Remember, what we're going to do is we're going to take two inputs and we're essentially trying to add them together with a sum digit going out and a carry digit going out. Now you'll see in our circuit diagram in the top right there that one of the first parts of a half adder is to use an AND gate to combine the signals from both of our main inputs here. So we can make an AND gate by putting 3 blocks across like that. We use 2 redstone torches, some dust, and another torch. Now down below, we're also going to want to combine these two signals using an OR gate, and so we're going to do that with repeaters, again, so the signal can't go back up the system and mess with our AND gate. And you'll see this repeater is going to get powered by the dust because of the block. We're going to have both of these repeaters run into blocks so that we can have one redstone wire going underneath connecting them. So now if either repeater turns on, then the redstone dust is going to turn on. Now comes the tricky part. Remember, we're going to run the output from this OR as well as the output from this AND. We're going to invert the output from this AND, and then we're going to run both of those into an AND gate. So that would look something like this. We invert it, we build another AND gate, and then we put our redstone torch out the front. Now there are a couple of problems with this setup, or rather inefficiencies. You see, you'll notice in our circuit diagram that the carry digit of the half adder should be coming from the output of this AND gate right here. And, well, you could do it, but it does look a bit tricky to try to get that signal out of here. Maybe you could have redstone dust going up that way, but then it connects with that, so you need a block there, and it just gets a little bit messy. The other thing you might notice is that this signal coming out of this torch is getting inverted 3 times. There's this dust, then a torch, another torch, and another torch. So we can actually cut out 2 of those without affecting the logic of the way the system works. So to make it a lot more efficient, what I've done is I've placed a redstone torch here, still powered by this redstone block, a block above it, and then to also power the block, I'm simply going to have this signal go around this way and run into it with a redstone repeater. And now if we take a redstone torch off of that, that should be the exact same, and that should give us our sum digit of the half adder. Now another thing I'm going to do is just shift this redstone dust one upwards so that we can position our redstone lamps. We can have one here and one here, and hopefully what we'll see is that this half adder now adds together the signal from the 2 levers. So right now 0 levers are on, which means our lamps are displaying 0 in binary 0, 0. Now if 1 lever is on, it'll display 1. So you see 0, 1, and it's the same if we switch it. So again, only 1 lever is on. This represents 0 and 1. Now if 2 levers are on, remember 2 in binary is going to be 1, 0, and so it should look exactly like this. And that's what happens. So that means our half adder in Minecraft is working exactly the way we want it to. Now it's time for the slightly beefier adder, which is the full adder. Now what a full adder is going to do is add together 3 different digits. So we can maybe represent those using P, Q, and R. We're going to be drawing another table here to describe what we want the full adder to do. So you can see I've drawn in all the possibilities for P, Q, and R, and our two outputs are going to be the carry and the sum. This is good because, remember, there are only 3 inputs here, which means the maximum answer we could possibly get is 3, and that's represented with a 1, 1 in binary. So we have just enough digits for this. Now let's try to fill in the rest of the table. Well, if none of them are on, in other words, all of them are off, like in this column, then we want it to give us the number 0. So we're going to have a 0 and a 0. If only one of them is on, like in this row, or this row, or this row, then we want the sum to be 1 and the carry to be 0, because the number 0, 1 in binary is the same as the number 1 in base 10. And then lastly, if 2 of them are on, like in this row, or this row, or this row, then we want it to give us the number 2 in binary, which, remember, is represented with a 1 and a 0. So we can fill that into our table. And we now know exactly what our full adder should give us for all 8 possible inputs we should give it. So now let's try to draw a circuit diagram for this and see exactly how we would connect together the things we've already learned in order to build a full adder. So we can have our P, our Q, and our R. And I think what we'll do first is use a half adder to add together P and Q. So I'm just going to do a little box and put in HA for half adder. Now remember, the half adder has 2 outputs. One of them is going to be a sum, and one of them is going to be a carry. Now, what we're going to do is take our sum and put it in another half adder with R. So we haven't used R yet. We can combine those 2 signals into another half adder. And again, that's going to have 2 outputs. We're going to have a sum and we're going to have a carry. Now, if we look at this closely, this sum digit down here is actually going to end up being the sum digit for the entire full adder. That's because we've added together P and Q, which of course are both digits. We've gotten the sum out, and then we've added R, so that means we've gotten the sum of all 3. Now let's think about the carry digit, because you might think we would connect these 2 with another half adder. But the problem with that is that a half adder has 2 outputs, and combined with the 1 output we already have down there, that's going to be too many for our table. In fact, if you think about it enough, only one of either C1 and C2 can be on at a time. That's because we only have 3 inputs, which means the maximum possible number they can add up to is obviously going to be 3. And so we're never going to get a situation where we're trying to add 2 up here and 2 down here to get 4, because 4 isn't something we can represent over on this side of the table. Instead, only one of these will carry or the other, and if one of them does, then we want the whole thing to. And so all we need to do, in fact, is have an OR gate out the front here, and this is going to be our final carry digit for the full adder. So we have our sum down here, and we have our carry up here. Alright, now back in Minecraft again, we're going to be trying to build a full adder now. We're taking 3 outputs, and we're trying to add all of them together. So we have 1, 2, 3, and we're essentially trying to count how many levers are turned on in the setup using 1 sum digit and 1 carry digit. Now we're going to start by doing a half adder between 2 of the digits, and that's actually going to be exactly identical to what I showed you a moment ago. We're going to have an AND gate on top, sort of like this. We're going to have an OR gate running underneath using these repeaters into these blocks. Now we're going to have a redstone wire going, I broke the repeater. We're going to have a redstone wire connecting them both for the OR gate, and then we're going to wire this part together to combine the signals from the OR gate and the AND gate to get our sum digit coming out this way. And then meanwhile, remember that this is going to be the carry digit from this half adder. Now, if you'll remember, the next step is going to be to take this carry and half add it with our third digit over there. So let's run it over here so that we can, in fact, end up doing the exact same thing we just did. So we can see we have our two pieces of redstone dust lined up, which means we can start building another half adder using an AND gate up top and an OR gate down below. Again, we're using repeaters running into blocks. And I'll try to break less stuff this time if I can help it. There we go. We run this redstone wire in, we put a torch, we build this sort of platform of blocks, put another block there. We're going to run this wire around and into there to combine the signals. Now this is going to actually be our final sum digit from the entire full adder. And then, remember the last step is to take the two carries and combine them in an OR, because that's going to essentially tell us, did we carry over or did we never end up doing that? And so we can just combine those two signals sort of like this. And if we want it to run into a redstone lamp, we might wire it up sort of like this. So let's test it out. Right now none of the levers are on, which means we get no sum and no carry. If we turn one lever on, we should see the sum turn on and the carry stay off. And that's going to be the same if this lever is on, or if only this lever is on. Now if two of the levers are on, then we're going to want to see the binary number 2 represented with those lamps, and that's going to be a 1 and a 0 if you'll remember. So let's try turning on these two, and you can see that the carry is on, the sum is off. It's the same with these two levers, or these two levers on the outside. And finally, the last thing to try is to turn on all 3 levers, which means we should get a binary number 3 coming out the other end, which is represented with a 1, 1. In other words, both lamps are on, and that's exactly what we've gotten here, so our full adder is fully operational. So now that we know how to build all of these different redstone logic gates and components in Minecraft, let's try to think about what order we would try to put them in to create a full calculator. To do that, I'm going to use an example problem. Let's say we're trying to do 3 plus 12. Now, as always, the first step is going to be to change these into binary. 3 is going to be represented like this because it's 2 plus 1. And then 12 is going to be represented like this because it's 8 plus 4. Now let's try stacking them on top of each other so that we can add them a little easier. We can draw our little line and our plus sign, and let's start adding. And in fact, the way our calculator is going to work is it's pretty much going to add exactly the same way we would. We start with the first digit of each number and we add them together. Now we have 2 digits here, and that's exactly what we've designed our half adder to do. So we're going to take these 2 digits, the first digit of each number, we're going to feed them into a half adder, and the sum from that is going to go into our answer. Remember, anything down here is essentially represented by those redstone lamps that we had in Minecraft. And then the carry is going to go over to the next column, and we're going to add it to the other 2 digits. Now what you'll notice is that we have 3 digits, and that's precisely what our full adder is supposed to do for us. So we're going to add together these 3 digits using our full adder, and again, the carry digit is always going to end up in our output with the redstone lamps, and the sum is going to, or rather the carry, is going to end up in the next column with the other digits. Now, it's essentially just a matter of repeating the process for however many digits we have. Again, we have 3 digits to add here, and so that's going to be a job for the full adder. Our sum digit goes down here, our carry digit goes over to the next column, and we can have one more full adder. We have the sum go down there into the output, and we have the carry go into the next column, but there's nothing else to add to, so in fact that carry can go straight into the output, which you'll see is also what happens in the game. Now, another interesting thing to notice here is that it's actually not too complicated to add more and more digits to this machine. You would need to add more full adders, and that would make it slower and bigger to be sure, but it would not necessarily be harder to build. So, now that we've done all that prep work, looking into redstone logic gates and half adders and full adders and all that, it's time to finally see exactly how this calculator works. So we're going to do the same example. We're going to try to add 3, 2 plus 1, and 12, which is 8 plus 4. So let's try to track how this works. Remember, we're going to start by using a half adder to add the first digits of each number. So we have the first one here and the first one here. You can see this first one runs into this wire, which goes straight down to here, and this is where that half adder begins. You can see this wire actually comes from over on that digit right there, which is the first digit of the other number, and they both connect into this half adder. Now remember, our sum digit is always going to go over into the answer, so you can see that's powering that first redstone lamp over there, whereas the carry digit is going to go on to get full added with 2 more digits. So it's going to go up here, and you can see here we have 3 more redstone wires lined up. This first one comes from the second digit of the first number, which I'm pointing at the wrong one, it's that one actually. And then this other one comes from the second digit of this number, which comes up in a little staircase this way. And now we have a full adder here, which is identical to the one I showed you down there. It's built exactly the same, just on some stone bricks in the air. We have our sum digit coming out this way. Again, those are always going to go into the answer, so that's the second redstone lamp over there. Then we also have the carry digit going into this block and down into that redstone dust that you might have seen for a moment, and it gets connected through this wire down into this full adder down here. Now again, there's 3 inputs, that one, this one, and that one. This one comes from the third digit of the first number, and this wire is a bit tougher to track, but you can see it sort of goes underneath that way, comes up here, and connects to the third digit of this number right here. So again, this is another full adder, exactly the same as the other ones. So the carry, which comes out of that redstone torch down there, it's powering this block, which is powering the redstone dust, which then gets sent on a journey all the way to the output, just like all the other sum digits. Then the carry, which is going into this block with the repeaters, is going to make its way up this way into our, I believe, third and last full adder. So that's the carry coming in there. Then this is going to be the fourth digit of the first number, which we can see coming in that way. And this one is the fourth digit of the second number. So it comes in through here. And we have our 3 inputs, as always, going into the full adder. Again, this full adder is what I've already shown you before. And the sum digit from that is going to go into a redstone torch down there. If I can see it, you can barely kind of see it down there. It runs over into the fourth digit of the answer, and because there are no more digits to add, this carry digit is going to again get sent all the way over here and into the last redstone lamp. And so remember, our example was adding 3 plus 12, which should make 15, which is comprised of 8 plus 4 plus 2 plus 1. And so that's how the entire calculator works. Now at this point, I know what you're saying. You're saying, potato, why didn't you make this thing more compact? Why does it kinda look like the spaghetti I ate for dinner last night? Why are your full adders so long? Why are they pointing that way instead of this way? Wouldn't that be more efficient? Well, first of all, what I would like to say is, have you ever considered the effect of your words on other people? But the other thing is that I've never really been great at making things compact. In fact, I'm pretty terrible at it. This machine is more of a proof of concept. It's something that I tried to figure out on my own using the knowledge I already had. And if you would like to try to make it more compact, more optimized, and possibly even work faster with all the redstone torches and redstone repeaters slowing it down, then I think that would be awesome, and I would love to see what you can come up with in the comment section. Now, the other thing you might be thinking is, well, isn't this kind of a stupid calculator? I mean, all it can do is add numbers together. I mean, it can't subtract, or can it? Well, there actually is a way to make calculators subtract, and it's quite similar to adding once it comes down to it. However, that's going to have to be the topic of another video, since I need to completely figure out the details before making that. Anyways, that's going to be it for this video. If you do have any questions, feel free to leave them in the comments section. I would love to see your thoughts on this whole thing and what you managed to do with it. But other than that, that's all I have for you today. Have a great rest of your day. Bye-bye. See, what's really fun is when you switch between the numbers 15 and 16 by like adding and subtracting one. Watch this. Oh, do 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 do. And if you turn it off, do 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 do.